So in this first lesson for homework packet 3.2, this is lesson 3.2a, we are going to take a look at solving polynomials by factoring. So let's first remind ourselves what a polynomial is. We've been working in the previous homework packet with linear and quadratic equations. Now, technically linear and quadratic equations are polynomials, but when does it come to the point where we don't call it linear anymore, we don't call it quadratic anymore, but we call it a polynomial? A linear equation is one in which it has an x term, no exponent on it. Well, technically it's x to the 1, but there's no x squared, x third, x fourth, so on and so forth. Quadratic, we do one step higher. It's something that has an x squared term on it. So linear is x, quadratic has the x and x squared, and if I have an equation with anything higher than x squared, I'm going to just call it a polynomial. So I've got some examples of that over here. I got 4x to the 5th minus 3x to the 3rd plus 6x minus 5 equals 0. I've got 3 examples of polynomials. All of them have powers. Their greatest exponent power is bigger than 2, so it's bigger than a quadratic. Now, we have this thing called the fundamental theorem of algebra that simply says this for our use where we're at with solving polynomials. There's more to it, but where we're at, here's what it simply communicates. The fundamental theorem of algebra simply communicates that the number of solutions you can expect from a polynomial is equal to the highest exponent value. So if I look at the highest exponent value in this first equation, it's a 5. So I expect to get 5 solutions. In this next one here, highest exponent value is 3, so I expect to get 3 solutions. And lastly, this one here has an exponent of 4, so I expect to get 4 solutions. Now there are some intricacies to this, but that is the basic gist of the fundamental theorem of algebra. So keep that in mind as we now look at solving polynomials so that you can anticipate how many solutions you expect to get when we solve these. So here's our first example of a polynomial that we need to solve. We'll notice that it's an x to the 3rd equation, so I expect to get 3 solutions. Okay. Now we want to solve this through the process of factoring. There's a step to factoring, though, that we need to always look at with polynomials that we're not normally used to looking at, and that is this. Looking at every term. Now remember, terms are separated by pluses and minuses. Okay. Right now this is in standard form. I have 3 terms in standard form, and I want to put it in factored form. But what I want to do first is I want to look and see, is there anything that every term has in common? And what I see is that every term here has an x in it. So what I'm going to do is I'm going to factor the x out front and see what I have left over. Now, this type of factoring here, when I'm factoring an x out front, is like undoing distribution. It would be like asking what is left here, so that if I brought the x back into every term, I would end up looking like my original. Well, to do that, what I'm essentially doing by factoring the x out is dividing it out. So if I divide x out of x to the 3rd, I'm left with x squared. If I divide x out of 2x squared, I'm left with 2x. And if I divide x out of the negative 24x, I'm left with negative 24. So I took an x out of every term and I put it in the front. Okay. So now I have this, which was written in standard form, written in partial factored form because I have one piece times another piece. However, I think I can factor this piece left here a little bit more. If we recall from our previous homework packet, we've got a quadratic here that you can factor into 2 binomials. Because it's x squared, I know I can just do x and x because x times x is x squared. But then what numbers go here and here? Well, we've got to figure out numbers that multiply to negative 24 and add to 2. Multiply to negative 24 and add to 2. I believe that's going to be a positive 6 and a negative 4. Yeah, negative 4 times 6 is equal to negative 24, and negative 4 plus 6 gets me the 2. So there it is. We are now in full factored form, and what you're going to notice is in full factored form, I have 3 pieces multiplied together. I have 3 factors. Well, it makes sense because I expect 3 solutions. So one solution comes from each of the factors. So let's do the ones that we're used to. Okay. I expect 3 solutions. Since I have 3 factors multiplying together to equal 0, I know that my solutions to this equation are simply what makes each of these factors 0. What makes x plus 6 0? Negative 6, because negative 6 plus 6 is 0. What makes x minus 4 0? Well, a 4 does, because 4 minus 4 is 0. And lastly, what makes x 0? Well, simply plugging in 0 to it. So whenever you have a lone x out front, that indicates that one of the solutions is 0. So here are the 3 solutions to my polynomial equation. Now remember, what do the solutions represent? These are the only 3 numbers that I can plug in to the x's here. I can plug in negative 6 to all of these x's, and this whole thing will equal 0. I can do the same thing with 4, and I can do the same thing with x equals 0. I can plug those in to all the x's and know that my equation is going to equal 0. So let's look at another example just to drill some of these concepts home. I've got another polynomial, and I notice that the highest exponent is a 3, so I expect 3 solutions. And the first thing that I need to do is I need to ask myself, is there something that every term has in common? And looking at that, I see that every term has an x in it again. If I divide or factor that x out, this first term is left with x squared. The second term here is left with negative 10x, and the last term here is left with plus 25. And that all equals 0. Okay. So after factoring this x out of every term, I notice that the piece that I have left in the parentheses is a quadratic, and we remember that we can factor quadratics up again into 2 binomials. So it's an x squared. That means I have an x here and an x here because x times x is x squared. But then I have to ask myself what 2 numbers multiply to 25 and add to negative 10. Multiply to 25 and add to negative 10. The only numbers that I know that multiply to 25 are 5 and 5. And if both of them are negative, I know I still end up with positive 25. But if I add those together, I know I'm going to get negative 10. Negative 5 times negative 5 is 25. And negative 5 plus negative 5 is the negative 10. So that worked out for us. Good. So as we expected, 3 solutions means I ended up with 3 factors here. So that means a solution comes from each of the factors. Now here's the interesting thing. Okay, what value of x makes this first piece 0? Well, 5 does, because 5 minus 5 is 0. What makes this second factor 0? Well, you'll notice it's 5 again. So do I just write 5 out again? Because I've already listed x equals 5 as one of my solutions. This is where we get into something called multiplicity. We'll talk about that in a second. So let's ignore the fact that we got that second 5 for a second. And let's look at this last factor here. What do I plug in to x to make x 0? Well, I just plug 0 in. So I actually only got 2 solutions, but I expected to get 3 solutions. So here's the deal with multiplicity. Sometimes we have repeated solutions with polynomials. And when we have repeated solutions, we call that multiplicity. So since I got x equals 5 as a solution from 2 different factors, I'm going to say that x equals 5 with multiplicity of 2. What that means is this 5 counts for 2 solutions, and the 0 is the third solution to get me to my expected 3 solutions. So I had a repeat solution. We call that a multiplicity of 2. If I had it repeat 2 times so that it appeared 3 times, I would say that it has a multiplicity of 3. So we still end up with our 3 solutions. It's just that one of them is counted twice to get to the 3 because of the fact that it occurs twice in our function in the factored form. So my solutions are 5 and 0, but the 5 has a multiplicity of 2. So let's look at one more example in solving polynomials by factoring. What you'll notice about this example first is that the highest exponent value I see is next to the 4th, so we expect 4 solutions. Secondly, my equation is not set equal to 0, but in order for factoring to be a useful method for solving a polynomial, it must be set equal to 0. So to do that, I'm simply going to add 15x squared to both sides. So I end up with 3x to the 4th minus 18x to the 3rd plus 15x squared is equal to 0. Great. Now that it's set equal to 0, I can ask that first question. Is there something that every term has in common? Now, interestingly enough, it's not just an x that every term has in common. It's an x squared that every term has in common. Plus, I believe every term has a factor of 3 in it. So I'm factoring out a 3x squared. And if I do that, what's left? If I divide 3x squared out of 3x to the 4th, I believe I'm left with x squared. If I factor 3x squared out of negative 18x to the 3rd, that's a minus. Divide 3 out of 18, I've got 6 left. Divide x squared out of x to the 3rd, it's just x left. And lastly, if I divide 3x squared out of 15x squared, 3 out of 15 leaves me with a 5, and x squared out of x squared, there's no x's left. So by factoring a 3x squared out front, I'm left with x squared minus 6x plus 5. A nice simple quadratic that I can now continue to factor into 2 binomials. So it's x squared here, which means x and x. Thankfully, this is pretty straightforward factoring. And then I have to ask myself, what 2 numbers multiply to 5 and add to negative 6? Multiply to 5 and add to negative 6. I think what's going to do that is a negative 1 and a negative 5. Negative 1 times negative 5 is equal to positive 5. Negative 1 plus negative 5 gets me to that negative 6. There it is. So it's x minus 1 and x minus 5. Negative 1 and negative 5. Great, I'm in fully factored form. Now, 4 solutions I expect, but I notice I only have 1, 2, 3 factored pieces. Well, realistically, I actually don't, because I can split up x squared even more. I can split that up into 3 times x, because that's what x squared is, times x minus 1 times x minus 5 is equal to 0. So realistically, I have 1 factor, 2 factor, 3 factor, and there's my 4th factor. This 3 out in the front here is just a coefficient that's floating around out front. So the question is, what are the solutions that come from each of those factors? What comes from the x minus 5? Well, x equals 5. so that 5 minus 5 gives me a 0 and makes my equation equal to 0. What about this next factor? Looks like that's going to be an x equals 1. Because 1 minus 1 is 0. Next, what comes from x? We've seen that anytime we have an x in the front, we know that our solution is 0. But notice this, I have two x's in front. So doesn't that 0 actually occur twice? Because it could fit into this x or this x, which is actually beneficial to us because we expect 4 solutions, but I only have 3 here. But with that argument, we see that this 0 actually has a multiplicity of 2. So the 0 counts for 2 solutions, the 5 and 1 are my other solutions. So these end up being my 4 solutions. The 0 counted twice.